Okay, we saw that we discussed last time that induction is actually an axiom. We believe it is true. We believe if with the first domino falls and all whenever a domino falls and the next one also falls, together these two will lead to the conclusion that all dominoes fall, right? But that's nonetheless an axiom. So we're going to use another axiom, which is just a restatement of this. So the important thing is you see the two seemingly very, very different statements, while they are actually exactly the same thing, right? So this is what you should learn. Moreover, in many of the classical texts on mathematics, induction is the proofs by inductions are given by in the form of this well-ordering principle, right? So if you read something which is written in the form of well-ordering principle, doesn't mean it's nothing that you that is something that you don't know. It's exactly induction. Okay. So the well-ordering principle is a very, very simple statement, and just like in many every other day, now you're going to see that these very, very simple statements, very simple statements, and it's just like not clear why, where would we use it, and where is what's the purpose of this, and then you will see the really great applications and usage of that. Okay. So this is so far the summary of what we studied, the induction principle, which says that if I prove that the statement, some proposition is true, some predicate is true about the first number, statements about all non-negative integers or all positive integers or all integers bigger, greater than or equal to 2 or something. If it say true about the first number, and I also know for a fact that whenever the statement, the predicate is true for the ith number, then it's also true for the I plus first number. Then together these two, if this conjunction, I can conclude that the statement is true, the predicate is true for all n. Okay, for all n in the universe of discourse. Generally, the universe of discourse is all non-negative integers or all positive integers, right? So we have seen examples of these the universe of discourse. For example, if you remember the ATM example, where we said, okay, all amounts greater than or equal to 7 can be generated or 8 can be generated, right? And then there were ICPs, where we said all amounts of greater than or equal to 12 can be generated using that thing, using some fixed denominations. So these things needs to be taken care of, right? You should know what are you talking about, right? What is the statement? Okay. How do you use induction to prove statements, right? We do two steps, the basis step and the inductive steps, right? The basis steps correspond to proving that the first domino falls, right? That we prove P of 0 is true, or P of 1 is true, or P of 8 is true, whatever the statement is talking about, right? And then we do the inductive step. The inductive step basically proves this infinitely many implications. P of I implies P of I plus 1 for all I greater than or equal to 0, right? So these are many implications. This is the journal n. So P of I, P of k, P of n is true, then P of n plus 1 is true, right? We apply a direct proof method or some kind of proof method for that. And then we talked about principle of strong induction last time. Strong induction or strong mathematical induction is basically a restatement of the whole thing, that we prove that P of 0 is true, that's the basis step of strong induction, and then we prove that if the statement is true for all I less than or equal to k, then it is also true for k plus 1. Okay, so it's slightly different implication. These are again infinitely many implications, but each implication is not P of I implies P of I plus 1, or P of k implies P of k plus 1. Is it P of I for all I between 0 and k? If that is true, then P of k plus 1 is also true. Okay, so we are doing now the principle of well ordering. Okay, it's a very simple statement. Again, you've seen it earlier. It just says that if you take any set of non-negative integers, any non-empty set of non-negative integers, then there must be a minimum. There must be a least element in that set. Okay, a very simple innocent statement, and let's see if you can actually find subsets which don't have minimum. So every word here is important. Okay, non-empty set. If you get an empty set of non-negative integers, can you find its minimum? Why can't you find a minimum? Sorry?
There are no elements in the set.
So why can't you find a minimum?
So because in order for there to be a minimum, there needs to be something which specifies some sort of order between those two elements.
Because you can't make any comparisons with
Yeah, but that's okay. So it's a correct thing, but generally speaking, you should go by definition. Yes.
In empty set, it has null and null are equivalent to being an integer.
What?
Null, it says that in non-empty set of non-negative integers. So null is not equivalent to being an integer.
What is not equal to an integer?
Null is
What is null?
Yeah, so because in an empty set,
What is null?
null corresponds to an empty set.
What is correspond to an empty set? There's nothing called null. Okay. Just go by the definition. What is a minimum?
Sir, I think this is saying that if we take any negative set, if we were to apply this to it, it wouldn't have a minimum. But if we take the empty set of the negative numbers, then there.
No.
But it's excluding that from the.
No. So what is a minimum? Just substitute the word. A minimum is an element or a number. If you're talking about numbers, an element that is smaller than all others. Okay, a number that is in this set. The minimum of a set would be a number, an element of this set, which is smaller than all, less than or equal to smaller than all other elements of this set. Right? Now, if I give you an empty set, there is no element there. Right? So, like you said, you can't compare it. There is what is it? Which is that element that is supposed to be the minimum, and what is it smaller than? Right? So, empty set. So, non-emptiness is a very important thing. Non-negative integrals, all of these words are important for this principle to hold. Okay. So, let's do some examples to see if this is actually if that makes sense. Right? What is the minimum of this set? What is the smallest, what element of this set? This is a non-empty set, right? Can you give me some examples of elements in this set? Quickly. Some element of this set? One. Some element of this set? Yes, more. Quickly.
0.
5, 6, all negative.
One example. -2. Any other example of this set?
5.
Okay. So, this is a non-empty set. Is there a minimum of this? Why not? Why isn't there a minimum of this set?
It's not, it has negative.
No, but that's a different thing. That would be saying, why doesn't principle of well ordering work on this? I'm just asking, why isn't there a minimum of this?
It's not a set of non-negative integers.
No, why isn't there a minimum? That's saying why principle of well ordering doesn't work. It doesn't satisfy the condition of principle of well ordering, but that doesn't exclude other sets to have minimum, right? Let's just please take this in mind. Here is a set. What is its minimum? Is it non-empty? Is it a set of non-negative integers? It's not a set of non-negative integers, right? Is there a minimum? Is there a minimum? Principle of well ordering doesn't work here, right? Remember, P implies Q is not equal to Q implies P. It's not if and only if. I can make this still there is a minimum, right? So I'm asking, why isn't there a minimum of this set? We'll see. So it doesn't contradict principle of well ordering, but why isn't there a minimum? Yes. That doesn't make sense. There are infinitely many numbers in this set. So let me make this set union Z plus. It has infinitely many elements, right? Does this set have infinitely many elements? Is there a minimum? Okay, so don't just say. So this is you made a correct statement, but it has nothing to do with the thing. Okay, go by definitions. Yes.
If we take a minimum number x, then we subtract one from it, we'll get another.
Okay. Yes.
Whenever we pick an element from the set, there is a number smaller than that.
Yes, there is no number that is smaller than all elements in this set, right? So the good constructive example is, if you suppose somebody claims that x is the minimum of this, some element x in this set is the minimum of this thing, then x minus 1 is an element of this set and it's even smaller than x. Okay, it's a good constructive proof by contradiction. Is this clear? There is no smallest element. Now, does it violate the principle of well ordering? Does it violate the principle of well ordering? Yes. Why? No, it doesn't violate. It does not violate the principle of well ordering. Principle of well ordering said, give me a set which is non-empty and which is of integers and non-negative integers, then I guarantee there will be a minimum. This doesn't have a minimum because we didn't fulfill the condition for the principle of well ordering. So it's not violated, right? The principle of well ordering doesn't talk about this set, doesn't make any claim about this set, right? Okay, what is the minimum of this set? All real numbers between 0 and 1, strictly between the open interval 0, 1. There are infinitely many there. We saw diagonalization, we proved that there are actually the second level of infinity. It's even more, it's an uncountable infinite set. But what is the minimum? Yeah. What? There is nothing called dx.
There doesn't exist a minimum because there are infinitely many irrational numbers between 0 and 1.
But that's not a thing, infinity. This is an infinite set. Let me make it an even bigger infinite set. You take all positive real numbers. Let's say even bigger infinite set. There's still negative 17.3 is this minimum. Don't state facts. Analyze the question. The question is about this fixed set, right? It has many good properties. This is written in black, right? The set is described in black ink. That is a true statement, but nothing to do with the question. Okay? Yes.
Whenever we pick the claim minimum, we can find an element midway between 0 and that is smaller than that.
Okay, so suppose some number is claimed to be a minimum, right? Yes, please.
This is not a closed set.
That has nothing to do with the statement. Now, is this a closed set? Closed and open. I use the word open interval, but that it's a true statement what you made, right? But nothing to do with the argument is not. It's not a valid argument. Yes.
So there is no smallest element because for whichever element you pick, you can divide it by some, let's say 10, and you can find a smaller element.
Yeah, so that's a good thing. Suppose somebody claims that this number r or x is the minimum of this set. Then x over 10 is still a number. If x is between 0 and 1, then x divided by 10 is also between 0 and 1, right? But x divided by 10 is strictly smaller than x, right? So that cannot be, x cannot be the minimum. If you take y to be the minimum, then I can divide y by 2 and that will be even smaller than your claimed minimum, right? So there is no minimum. Does it violate the principle of well ordering? Why not? Yeah, the principle of well ordering doesn't claim anything about sets which have non-integers, right? It may or may not have it. It is a set which has non-integers also, but does have minimum, right? Okay. So there is another word that I just want you to hear the word. So these mathematicians don't impress you. It's called infimum and supremum, right? Infimum is a number. So in this case, infimum of a set is the largest number that is smaller than all in the set. The largest number that is smaller than all elements of the set. So in this case, 0 is the minimum of this set. 0 is the infimum of this set. Okay, 0 is the largest such number such that any element of this set is bigger than 0, right? Negative 1 is also, every number here is bigger than negative 1, but negative 1 is not the largest such thing. Negative 0.3 is even larger than negative 1, and it's also smaller. 0 is that thing, and supremum is the smallest number that is bigger than all numbers in a set, right? It's called the supremum of a set. So in this case, typically mathematical analysis people, real analysis people would talk about the infimum of a set and the supremum of the set. This is really the boundary, and there this inward infinitesimal or whatever things comes in. Yes, please.
Sir, I think you mentioned it just does not violate the principle of well-ordering.
Yes, good. Okay, because principle of well-ordering talks about integers, right? It claims that if you give me a set of non-negative integers that is non-empty, I will show you a minimum, right? Now I gave it this set. I gave this claimant, this guy who claims this thing, I gave him this set. I didn't fulfill the condition. They said, give me a set of non-negative integers, in a non-empty set of non-negative integers. I'm only then responsible to give you the minimum. Here you didn't give me a set of non-negative integers, right? So it's real numbers. They may or may not have a minimum. Okay? Okay, so this doesn't have a minimum, but you know the word infimum and supremum, right? Okay. So 10, 13, the next thing is 3.9 plus 1 over 9. What is plus 1 over n, where n is all positive, any positive integer? What is the minimum of this? Give me some numbers in this set. Give me some number in this set. 3.9 plus 1, 3.9 plus 4. 3.9 plus 1 by 2 is, yeah, so 3.9 plus a half, 3.9 plus a quarter, 3.9 plus a fifth, 3.9 plus a sixth, all of these numbers are there, right? What is the smaller number, smallest number in this set? What is the smallest number? 3.9? 3.9, does 3.9 exist in this set? Is 3.9, that will be 3.9 plus 0, right? 3.9 plus 0 doesn't exist in this set. 4.9 is not the smallest. Yeah, 4.9 may exist, 3.9 plus 1.
So is 3.9 the infimum?
What is the smallest element? Does 3.9 exist in this set? Is it, so it cannot be the smallest. What is the smallest number? There isn't any smaller number, again, because if you show me a number, claim that this is the smallest number, that number will be 3.9 plus 1 over 19 million something. Then I would say, okay, 3.9 plus 1 over 19 million plus 1 is even smaller, because it's even smaller thing added to 3.9, right? So 3.9 is the infimum of this, but it's not the minimum. It doesn't exist in the set, right? It's not the set. This doesn't have a least element. There is no smallest element. Any number you claim to be a smallest, I can show you even smaller than that. Okay? And this doesn't violate the principle of well ordering, because this is not a set of non-integers, right? Okay. Here is a 1. 3.9 plus 1 over 9n, the same thing, but now it is the floor of that. The previous set, so all numbers here, but you take the floor of that. What is the minimum now? 3.9, 3. Is this 3? Does 4 exist in this set? Where is 4 in this set? Why is 4 there in this set? 3.9 plus 1 over 1 is 4.9, and the floor of that is 4. Does 5 exist in this set? Does 5 exist in this set? All numbers are less than or equal to 4.9. 4.9 is the biggest number here, right? If you ignore the ceiling. Think about this thing, okay? What is the biggest number and what's the smallest number? Smallest doesn't exist, the biggest is there, right? 3.9 plus 1 is the biggest number. So 3.9 plus 1 over 10. 3.9 plus 1 over 11 is 3.91 or something, right? 3.99, and the floor of that is 3. So that's the minimum number. Yes. So essentially this set only has 2 elements, okay? Because repetition doesn't matter in sets, right? So this set has only 2 elements, 3 and 9, 3 and 4. Yes.
So is the floor of any real number its infimum?
I don't know. Infimum is defined for a set. Okay, it's for a set, a collection of objects. Okay, so this is now a set of integers. It's non-empty and it's non-negative integers. So now principle of ordering is responsible to find me a minimum, right? So the minimum exists here. That's simple principle of ordering, nothing more than that, right? Then that's why it's very important to see, like, why, what does it have to do with induction? Where is implication? Where is this infinitely many implication? Where is the basis step or the base case? Where is the principle of mathematical induction? Where is the statement about all integers, right? Where is that proposition or the infinitely many propositions or the predicate about all positive integers, right? Nothing of that sort is obvious here, but this is what we're going to do. Remember, recall this thing. That's the principle of ordering. Any non-empty, non-negative integer set has a minimum. That's a well-ordering principle. Induction, we know what's induction. You know this is the proof of by induction. We prove the basis step and we prove the inductive step. And together these two give us the conclude that for all n, p of n is true. Okay. So now I'm going to argue that induction makes sense because of principle of well-ordering, or induction works because of principle of well-ordering, right? Another way of looking at induction, another way. Can anyone see some connection between the two statements? These two statements? Do you guys see any connection between them? Do you see the distance between these two statements? Okay. So let's just do, yes, please.
So the base case essentially we're trying to prove for the smallest element.
Something like that, yes.
And then for each subsequent case, if we just do the plus 1, then we prove all.
Okay. So let's see, we will do this. Suppose I have proven something. Suppose this is a principle of induction, right? I've highlighted what is like what we call the basis step, and how do we achieve the truth of p of 0? That's what we call basis of step. And how do we achieve these infinitely many implications? That's what we call inductive steps. And together these two, the conjunction of these two implies that the statement is true about all integers, right? So suppose I have proved some statement, some proposition p about all integers using induction. That means I have given proofs of two statements. I have proved two things. One is that p of 0 is true, and second is for all k greater than or equal to 0, or whatever the base case is, the base the starting statement, the first domino is for all k, p of k implies p of k plus 1. So I have proven 1 and 2. Okay, remember this thing. Suppose I have given a proof by induction and still the statement isn't true. So suppose induction doesn't work, right? Just for the sake of argument, assume that induction is just a nonsense statement, doesn't make any sense. Okay, so please pay attention to every single word here. Okay, suppose I have proven p of 0 is true, and I have proven that for all k, p of k implies p of k plus 1 is true. Still there exists for all n p of n isn't true. Suppose for all n p of n isn't true. Okay, that means when I say for all n p of n isn't true, that means there is an I such that not p of I, right? So there exists a n such that not p of n. There exists a counter example to the for all n p of n statement. Does it make sense? Yes, there exists a counter example. So that means I have proven 1 and 2, still induction doesn't work, still their statement isn't true. Is this clear? Yes, so there are certain counter examples for all n p of n. Okay, so let's take the set of all counter examples, the indices of all counter example. So collect all k's. I'm making a set S, that is the set of all k for which p of k isn't true. Okay, the set of all k for which p of k isn't true. Now, can S be empty? Can S be empty? S is not empty. We assumed S isn't empty. We assumed that there are some counterexamples, right? So this is the set of all counterexamples. There must be at least one counterexample. Otherwise, for all n p of n will be true. Okay, for all k p of k will be true. So there is some element in this S, right? Remember, the set S is the set of all indices k, all dominoes indices k, all what is it called, all non-negative integer for which p is not true. Okay, so it's a set of non-negative integers and it is not empty. Principle of L ordering says that there must be a smallest element of this set, right? So let's say m is the least element of this set S, right? So in this infinitely many statements p1, p2, p0, p1, p2, p3, pi of these infinitely many statements, this pk, pm is the first counterexample. Is the first counterexample. Remember, please understand this thing. If I'm making this statement, this means p of 1 is true and p of 2 is true, p of 0 is true and p of 3 is true. You know, just goes on, right? That's what. Now, if this statement isn't true, then there must be some false statement. One of these propositions, at least one of these propositions must be false. Okay? So this p of m is that first proposition which is false, right? So all of these are true. This is the first one which is false. Okay? So if the statement isn't true, then there must be counterexample. This is the least counterexample. Yes?
The least counterexample becomes
the smallest, the first counterexample. It's a sequence of, I remember I told you, a universally quantified statement about all integers can be thought of as a sequence of propositions, right? And so in that sequence is the first proposition that isn't true. Yes, please. Good. These look at this statement. This statement is not about principle of L ordering, is making a claim about some type of sets. No, we saw examples where it didn't work. So what is real number? What is, I don't know. So look at this. What is the minimum of this set? You know this set? How do you write Q? The set of rational numbers. What is the minimum of this? This is not, it's a set of rational numbers. Not all real numbers are there. It's a countable set. What is the minimum of this? Huh? No, there's no minimum. And we also saw this thing. What's the minimum of this? Yeah, what's the minimum of this? So it has nothing to do with.
Can we replace positive integer with positive 2 decimal places?
Positive 2 decimal places. Oh, that's what you say. Positive, what is 2 decimal places?
1 decimal, 1.1.
Positive 1.1, 1.2. Yes, maybe you can. Because you can just take this is just, you multiply everything by 10, they will become positive integers and the thing will work, right? And the minimum will be just, you divide it by 10 again. Okay, so let m be the least element of, m is the first counterexample, the index of the first counterexample of these among these infinitely many statements, okay? So now, why does m exist? Because of principle of L ordering. Okay, now let's see what is the value of m. What are possible values of m? Can m be 0? There is, so out of these, all of these statements, at least one is false. Can the first one be false? Right? Why not? Because we have demonstrated that p of 0 is true. That's an explicitly given thing. P of 0 is true. Okay, so p of m is false because m is in the set S, but m cannot be 0. m cannot be 0 because because of 1, because of this statement 1. We said p of 0 is true. So maybe m is 1 or 2 or 3 or 4 or 5, right? So p of m is some number, but what is p of m minus 1? What is p of m minus 1? P of m minus 1 is true. Why? Because m is the least element of the set S. M is the first counterexample. Everything to the left of m, before m, are true propositions. Okay, so p of m minus 1 is the true, p of m minus 2 is true, p of m minus 19 is true, all of them are true. Okay? So p of m minus 1 is true and p of m is false. That's what we so far get. If induction doesn't work, then p of m minus 1 is true and p of m minus 1 is false. And that's already a contradiction, because p of m minus 1 is true and p of m is false. But in statement 2, in the inductive step of induction, we have proven that if m minus 1 is true, then m should also be true. So we have proven that this implication is true. But how can this implication be true when p of m minus 1 is true and p of m is false? True and false, true implies false is false. But we know this is true, right? That's a contradiction. Okay, this is the way, this is like you can, it's not, it's a deep statement. Okay, take some time to digest it. Take your time, spend a few seconds on it to understand what is going on. Yes, this thing. Okay, okay, so look at, so in this analogy I've been telling you that, okay, let's say p of m is the first statement that is true. What does the first mean? In a sequence, the first means everything before that are false, right? If that's the first statement true, then everything before that is false. Here we said p of m is the first statement which is false. Then everything before that, p of m minus 1, p of m minus 2, p of m minus 17, all of them must be true. Okay. Okay. So let's just use just give you an application of p of the principle of ordering. Now, typically the induction proof can be written like this. The proof is by induction on k. P of 0 is true when k is 0 or k is 1 is true, a basis step, and then p of k implies p of k plus 1 is true for all k, right? That's one way. The other way of doing it is just saying that, okay, suppose the statement is not true. That's for all k p of k, for all n p of n. Suppose that is not true, then there is a counterexample, right? There is a k for which p is not true. Take the least counterexample. Take the minimum counterexample, right? Take the smallest counterexample. Then you prove that the smallest counterexample cannot be 0. That's actually, you replicate the basis step proof, and then you prove that if p of k is false, it's the least counterexample, p of k is true, right? So then you prove the what is it called, the contrapositive of that statement, right? If p of k implies p of k plus 1, that we prove, you replicate exactly the induction proof. In reading, some people find it easier to say. It's typically in classical mathematical texts, mostly British texts, people write this well ordering way of writing. This more computational, more algorithmic way of doing constructive proof is that induction work, which is in your choice, whichever you want to do. It's exactly the same thing. Okay, I showed you the thing. Okay, the division algorithm, big word, simple statement, simple principle. If you take any integer, and you take any non-negative integer or any positive integer d, sorry, positive, not non-negative, any positive integer d, you divide a by d, you will get a quotient and a remainder. Okay, the division algorithm says, which is a theorem, it's called division algorithm because it actually gives us that long division algorithm. So it says that the quotient and the remainders do exist. Whenever you divide an integer by another positive integer, you must get some quotient and some remainder. It cannot happen that doesn't exist, it's undefined, that cannot happen. Moreover, it says unique quotient and remainder. It can never happen that if you divide something by some number, I will get different answer, then you will get a different answer, right? We can't say this. If you take a number, let's say if you take a number a and you raise it to, you apply, rather than the division algorithm, you apply the root algorithm, Is there a unique answer to this thing? Is there a unique answer to this thing? Every A and D, is there a unique answer? For every A and D in a positive D, is there a unique answer? Right? So if you take A equals 4 and D equals 2, the answer is both 2 and negative 2. Right? So this one says no, there is a unique answer. Whenever you do a division, you will get two things, the remainder and the quotient, both of them will be unique. Okay, so the terminology is Q is called the quotient, R is the remainder, D is the divisor, A is the dividend. And so what actually it says, that if you look at the real line and you divide them by into these segments or intervals of D, right, intervals of length D, where that's the divisor, and so this A is somewhere in this line, every number is in somewhere in this line, right, it's integers, A is an integer, it's somewhere in this line. The quotient is the block where it belongs. How many steps did you take from 0, how many blocks of D, how many intervals of D you passed before reaching this A, right, in this direction or that direction. And the remainder is actually the offset. How far are you from the boundaries? Okay, so this is what A is equal to DQ plus R means. Okay, so let's look at this. So when 11 is the dividend and 5 is the divisor, what do I get? What's the quotient? When I divide 11 by 5, what's the quotient? 2. And what's the remainder? Right, I can write it is 5 times 2 plus 1. Right, 5 times 2 plus 1, that's what this statement says. There is unique D and Q such that A can be written as D times Q plus R. There is a unique Q and R such that A can be written as D times Q plus R. Q is the quotient, R is the remainder. Okay, so 11 is called the quotient, it's written as div 5, and R is called, the remainder is called mod 5, right? When we do number theory, we will talk about that thing, this thing, okay? And this is about any A, right? Not positive, not negative. When I divide negative 11 by 5, what do I get? When I divide negative 11 by 5, what should be D, Q and R? Negative 11 is 5 times negative 3, and 5 times negative 3 plus 4, right? So 4 is the remainder and negative 3 is the quotient. Make sense? Okay. Or in this case, so D is what? 11 is what is Q? Q is A is negative 11. If these are length, what is D? D is 5, right? So this is negative 5. Where will be negative 11? Where will be negative 11? This is negative 5. This is negative 10. So it's in the third block, right? So the quotient is negative 3. Where is it in the third block? Plus 4. Okay. Negative 11.
It would be the third plus 4.
The third plus 4?
3D, right? We're talking about
yeah, negative 3D plus 4. Okay. Yes. So whatever that is, it should be clear to all of you, right? Here is how you look at division. The division algorithm is, if you have a positive A, you repeatedly subtract D from A so that you get something between 0 and D, right? Strictly less than D, less than or equal to 0, or greater than or equal to 0. Yes? No, so this statement is about D being a positive integer. The divisor has to be a positive integer.
Yeah, but the remainder to be that.
Sorry?
The remainder has to be positive. So it can't
The remainder will be between 0 and D. What?
I just answered the question.
Okay. So you understood the question. Repeat. So adding division is basically for positive number a dividing by d basically means you repeatedly you repeatedly subtract d from it until you get something smaller than d, right? Less than between positive but smaller than d. Okay, and for negative a you repeatedly add d until you get something between what is it called, between something get positive less than d, right? You keep on adding d, it will go higher and higher. The moment you get to the block, the positive thing, you will get that thing. Okay, so let's prove it using mathematical induction. Okay, I don't know, there should have been some pauses here, but let's see. Okay, the proof is very simple. Okay, it's a very simple thing. So I'm going to prove this statement says there is a unique quotient and remainder. I'm going to prove that there exists a quotient and remainder. The uniqueness proof is on the next slide. Okay, so let's just focus on existence. A is a number, a minus a is an integer, then what is a minus dq? Well, depending on q, d is given positive integer, so if q is an integer, then it is also an integer, right? So for each possible integer q, you take the set a minus d times 1, a times 2, a minus 2d, a minus 4d, a minus 5d, a plus 4d, a plus 5d, a plus 19d, and all of them. You take all these integers, right? If a is an integer, d is an integer, q is an integer, then a minus dq is always an integer. Out of all these integers, whichever are positive, you take that set S, right? You take all a minus dq's that are positive. For all q's which are positive, you take the set S. It's a set of positive non-negative integers. It's non-empty. Is S non-empty? If a is an integer and d is not 0, right, d is a positive integer, so then a minus d1 is either a is bigger than a is positive or negative, so either a minus d 1d will be positive and will in this set, or a plus 1d will be positive and in this set, right? So it should be there somewhere. Okay, it should be this set is non-empty, there must be something. Now if it is a non-empty set of non-negative integer, then there must be a minimum, right? So let's say r a minus dq naught is the minimum, so the minimum comes from some integer q naught, right? That is r, let's say that's the minimum of this set. Okay, so if this is the minimum, can r be, will r be less than d or bigger than d? Can r be less than d? Can r be bigger than d? Greater than or equal to d. If r is bigger than d, then I can actually subtract one more d from it and still get something between positive and less than d, right? So I can get something even smaller that is positive, and it's also, so if r is greater than d, then I can take a minus d times q naught plus 1, still get some number r minus d, which is also non-negative. Then r minus d should have been there, right? So r is less than d, right? R is less than d, and so I got this thing that this q naught is the one that exists. A can be written as d times q naught plus r, right? A is can be written as d times q naught plus r. So I got that there exists some q naught and some r such that a can be written as the quotient times divisor plus the remainder. Okay, and the divisor, basically the remainder uniqueness of the d q naught, q and r just follows from this thing. Suppose there are two quotients, d times q1 plus r1 is equal to a, and d times q2 plus r2 is equal to a, right? Both r1 and r2 are less than or equal to d, right? Suppose both r1 and r2 are less than or equal to d, then you say, okay, the divisor has to be less than or equal to, so d is less than or equal to r1 and less than or equal to r2, right? And this gives us that d actually divides r1 minus r2, right? And just work it out. Okay, everything is written on the slides. I don't want to go in this thing more. Okay, so that was induction that we wanted to, we'll build upon inductive definitions that we will do when we do recurrence relation in 1 week. You will see much more of inductive definition and many more usage of recursive algorithm and recursive definitions of sets and sequences and algorithms and functions. All of this we'll discuss in detail. Okay. Okay. Okay, there should be Dr. Malik Jahan name here, but this is now the cool part. The coolest part of the course is here. Okay, the most beautiful part of the course until now is here. Later we see much more better parts of this. Graphs are even beautiful. Combinatorial proofs are beautiful, and binomial theorem is also beautiful. Recurrence is also beautiful. Trees and number theory, cryptography is even the best. So we'll see. So far the best thing, okay, the very, very important thing, combinatorics, right? Remember, combinatorics is the art of counting, right? How to count, how to count. A lot of application you won't be able to comprehend, you will be able to like appreciate fully why, where are these useful, right? But it has a lot of application in computer science. You see, this is very closely related to algorithm. You must have seen combinatorial. Can you please stop this? Combinatorial algorithm, combinatorial optimization. Okay, and optimization in. Can you please close the windows? Both of them, okay. Okay. Here are some applications. This is the slide is like from the lecture 1, our application thing, right? The only subject that count is actually math, right? So combinatorics is that branch of mathematics that counts, okay? So in hardware design, in system design, you always want to compute the probability of a component failing, right? And probability is just a fancy way of counting, right? It's a fancy way, a more systematic way of counting, right? So if I rephrase the question, this probability question like this, in how many scenarios, in how many possible scenarios the component fails, that is a counting question. Versus if I say what is the probability of a component or this component failing, is the probability version of that question. Okay, so it's just counting. How long does a program take? What is the runtime of a computer program? What's the runtime of an algorithm, right? The runtime is actually how many question, how many operations, how many clock cycle does this program require for execution, right? It's a counting question, right? It's also very useful in designing algorithm. Okay, when you actually come up with a design algorithm, I'm going to show you some examples of this. Okay, so this is why counting. That's how many questions. Remember, this is sorting algorithm. We discussed briefly the selection sort algorithm, right? Repeatedly finding the minimum of the remaining arrays. How many times this blue statement is executed, this comparison statement is executed. That's how we count the runtime. That's why we compute the runtime of an algorithm, right? We count the number of elementary operations performed. We don't look at the clock time, because the clock time depends on whether you run it on this computer or a bigger computer, whether it's in this operating system or that operating system. It's depending on many other factors. So clock time is not a good measure of judging the efficiency of an algorithm, right? The better question to ask about algorithms is how many operations are performed, right? That is giving you a platform independent answer. Okay, so how many comparisons are performed? You see, counting questions. It's a counting question. How many comparisons are performed? Sorry? Yeah, that's not important. The answer is never important. Question is important. Okay, you see the how many questions. Okay, we know how to do it. We did it when we did sequences and sums. We talked about this, right? It's a triangular number, not n squared, in this n into n minus 1 over 2. This is what we saw in programming and algorithm design. It helps a lot, right? What should be the size of data structure? How many elements do I need in the array? What should be the number elements? You guys are doing data structures in parallel now, right? How many nodes in the linked list? How many nodes in a binary search tree? You don't do? How many? What should be the length of the array? What should be the length of an array for your program to work? right? The length of the array, how many iterations in a loop, right? All of these are just combinatorial question, counting questions. In testing, in program analysis and program testing, software verification, so how many different types of input, how many different inputs should I generate to run to be sure that the algorithm is test cases. Remember test cases? In programming you do test cases, right? For dry runs and wet test or running test. How many test cases should be there to be sure that the program is highly accurate? Okay. In probability, I told you it's randomized algorithm, probabilistic algorithms. What is the runtime of algorithm? What is the chances a component will fail, a network link will fail? It's all actually counting questions. And then combinatorial proof is a beautiful book called Proof That Really Counts. Okay, that is a counting based proof. I'm going to give you a few examples of this later. All of these questions in security, in cyber security, in system security, software security, in all of these kind of questions we always ask. How many bit strings of length n are there, how many valid passwords are there, how many different IPs are there, how many so remember, can you please stop this thing? How many so you guys know MTags, right? This motorway E-tags and MTag. At some point they were doing they were designing this stuff, and they had this so they underestimated the number of possible cars that could go through the motorway. So there were just one motorway at that time when they started, this one between Lahore and Islamabad, and then this was a big issue, right? And then they had to redesign this thing. Now the pass, what it's called, easy pass, easy tag, right? What is it called here? MTag. Okay, so all of these things, we are going to do some of these techniques for counting, so most popular, most useful techniques, and so let's begin with those. Okay, so and this, all of them you must have seen, okay? So suppose you have 9 long sleeve shirts and 8 short sleeve shirts. Right? Hopefully my counting is okay and my eyesight is good enough. So I tried to count them. There, this many. How many choices do you have for a shirt on a given day? Okay. What is? How many choices do you have? 9 plus 8, right? That's important. 9 plus 8. Why 9 plus 8? Why 9 plus 8 choices? Yeah, why 9 plus 8 choices? Don't throw facts at me. Why 9 plus 8 choices? The general principle says the following. So in this case, we have number of cards. The number of cards of the same suit will be 10 over 4. The ceiling of 10 over 4. Okay. And the 10 over 4 is 3. The ceiling. Okay. If I take any set of 13 people, there must be at least 2. So I can choose one of the 9 long sleeves one, or one of the 8 the short sleeves one, right? And that will give me, that's why I have 9 plus 8 choice, and that's called the sum rule. Okay? If a task, understand this thing please, okay? It's a very simple thing, and it's so simple, so easy that people just and it's not like such useful for many problem unless it's in combination with other things. Okay, so I'm going to give you example where this is the only way to do stuff. Okay, but that's in conjunction with other thing. If there is a task that I have to do, if the task can be done in either one of the n1 ways or one of the n2 ways, then I can say that the task can be done in n1 plus n2 ways. Okay, so in the previous example, the task is picking up a shirt. It can be done in choosing one of the 9 long sleeve shirts, that's n1, or one of the 8 short sleeve shirts, and so the total choices is n1 plus n2, that's 8 plus 9 or whatever, right? In the set theory, it basically says the following. If you have two, this either and or are very important there. If you have two disjoint sets we have zero intersection, empty intersection, no, not intersecting, no overlap, right? Then the cardinality of the union is equal to the sum of the cardinalities. Okay, does it make sense? Well, how many elements are there in A or B, or if I take the union of A and B, how many elements will be there? Well, all elements of A will be there and all elements of B will be there. Nothing from outside A, both A or B will be there, and there is nothing in both A and B, right? So I can just count the number of elements in the yellow area and the number of elements in the green area, and that will be the cardinality of the union. Okay? Okay, so let's do a few examples. Suppose I have 32 students in one section of this course and 35 students in another section of this course, and I give out only one A. How many choices do I have? 32 plus 35, right? That's by the sum rule. Giving out an A is a task that I have to do. I can do it in one of the 32 ways of choosing a person from section 1, or one of the 35 ways for choosing a person from section 2, and that's why the total choices I have is 32 plus 35. Okay, suppose you have to choose a project from either 4 software development projects or 5 research projects. How many choices do you have? Right? In many different courses, we give you different types of projects on this topic or that topic or this topic, and then in each one there are multiple options. You can choose either of them. So you have 4 plus 5 choices to choose a project, right? Okay, so the sum rule is extremely easy, but understanding it's important to understand what are the sets we are talking about, and to make sure that they are disjoint. That is slightly sometimes tricky, so you have to be careful. Okay, and we generally construct sets. Okay, it's not given like this. We'll see in the next slide. Okay, journal version of sum rule is basically if a task can be done in n1 different ways, in one of the n1 ways, or one of the n2 other set of ways, or one of the n3 another set of ways, and so on, then the total task can be done in n1 plus n2 plus n3 plus n4 plus so on 2 ways, right? And the set theoretic version of this thing is if you have k sets or n sets which are pairwise disjoints, then the cardinality of the union is equal to the sum of the cardinalities. Okay, so here is a good question. I'm going to give you a 4 by 4 square. Does it look like a square? No, that's because this aspect ratio is different. It's totally good square there, and it's my screen. I give you a 4 by 4 square, and I ask you to divide it into unit squares by parallel lines, 16 unit squares. Okay, so divide it into 16 unit squares like this. And my question is, how many squares are there now in this picture? 16 unit squares. There are 2 by 2 squares, no? Aren't there 4 by 4 squares? So how many squares, not answers, how many squares are there in total? Now remember this thing, I want to tell you this thing. Everyone knows sum rule, right? The addition rule, the sum rule for counting. It's a counting question. Sets are not given to you. You have to now find out or define or some way, not generally, not very explicitly, but one way or the other you have to construct those sets and say it's a union and make sure they are disjoint, and then count, add the cardinalities. Okay, this one. Yeah, we don't divide, we count them separately, right? We split. Okay, what is a task? The task is, let's say, picking up a square, right? So how many different squares can you pick up? Can you choose, right? How many different squares can you choose? That's a question. So I can divide them into, okay, so I define AK to be the number of squares of your length k, right? So k by k squares are added all squares of length k by k of dimensions k by k are added into ak, right? So is it clear? And then my answer is, what should I do? Where is the sum rule? A square could be either in A1, in A2, A3, some squares in A3, some squares in A4. Is A4 and A3 disjoint? Can there be a square that is both in A4 and A3? Why not? Because squares in A3 are 3 by 3 squares. Squares in A4 are 4 by 4 squares. So no square can be in both of them. So I just add the cardinalities of A1, A2, A3. That is my answer, right? A1 plus A2 plus A3 plus A3, the cardinalities. Is this clear? Yes? What is A1? How many squares of length 1 are there? 16. How many squares of length 3?
3, 4.
So this is a 3 by 3 square. You slide it here, that's another 3 by 3 square, and then you slide it up, you get 2 more. So it's a 4, I think. How many 2 by 2 squares are there? 9, right? So this is 2 by 2, the first one, bottom right, bottom left. Then you go one step here, another one, then one step here, another one, then one step up and another step up. So it's 3 by 3, 9 squares, right? How many 4 by 4 squares are there? How many 4 by 4 squares are there? 1, right? This one global square, right? So you just add them and you get this number, total number of squares. Got it? Okay. Suppose I roll a red die so red and blue dice. So 2 dice are rolled, and how many outcomes I will get that both dice show different values? The red and the blue values are different. Not answer, the method. Okay, where is set here? Where is sum rule? What is the task, and what is the different ways of doing the task and other stuff? Not answer. Yes. Is this statement clear? I get any 12 numbers in. Yeah, but that doesn't answer the question. These are all the outcomes where the dice show different values. Yes? Is 1 1 here? Is 2 2 there? And the red one shows 2, and also the blue one shows 2. Is that there? 1 1 is there? No. So these are how to count them in general. Give me some method. Yes. Yeah. No, some rules. We have to look at this thing. Everybody can have very different GPAs. Okay. How would you do that? Please go with problem sets and the quizzes in these ICPs. Do them, every single one of them, in quite detail. Okay, not just the sheet thing. In detail to work it out. Yes, please.
Sir, can we have 10 intervals of 0.1 which?
Okay. Yes, that's.
Form sets based on one dice. Whatever
One.
value is on one dice. So if there's one, then you can have all possibilities of the other with that one. Then you would get 6 sets.
Yeah. To define AI to be the set of all outcomes, AI is the set of all outcomes where the red die show I and the blue die shows something else. Make sense? So A1 is basically the first row. All outcomes written here in the first row, right? A2 is all outcomes written here in the second row. The red die shows a 2 and the blue die shows something other than 2, right? So 1, 4, 3, 4, 5 or 6. Does this make sense? And so now my question is, how many total outcomes where both dice disagree or have different values is basically A1 plus A2 plus A3 plus A4 and so on, right? These are disjoint sets. That's why their union will be just the sum of their cardinalities. Is it clear? Okay. So the answer is whatever, 5 times 6, I guess, 30. Okay. So that's called the sum rule. Okay, so okay.
How about we do it?
In the previous question, there was only one set. The
No.
AI was only one set.
A1 was one set, A1 was one set, A2 was another set, A3 was another set. Yeah. So AI was actually the first row, A1 was the first row, AI is the ith row. Yeah, okay. So we talked about sum rules, okay. So now next we are talking about product rule, okay. Again, this you should have seen. Now, okay, so something is wrong with these slides. Suppose you have 9 shirts and 6 pairs of pants. So how many choices would you have for an outfit? 9 times 6, right? Why isn't it 9 plus 6? Previously it was, what's the syntactic difference between this slide and that slide where you answered 9 plus 8? No, that is a solution. Syntactic difference between these things, other than 9 and 6 and 9 and 8, those were numbers.
So we have to pick a shirt and a pant.
Yeah. So there you have to pick an outfit, not a whole dress, right? Not just a shirt, right? So that was kind of or, and this is kind of and, right? So you have 9 times 6 choices of different outfit, right? The blue shirt and the black pants, and the blue shirt and the gray pants, and the blue shirt and the light gray pants, and all those kind of stuff. Okay. Suppose you decide to go in full monkey suit. How many choices you have, right? So you have 9 pairs of pants, no, 6 pants, 9 shirts, and 4 ties. Ever wore a tie? This is one of the same thing. I remember my advisor won the Abel Prize, and I used to manage his emails and other things. So I called him, "Hey, Andre, you won the Abel Prize." Abel Prize is it's $1 million prize, and it's because mathematics doesn't have Nobel Prize, so it's counted as actually it's much more bigger value than Nobel Prize, because it's kind of a lifetime achievement award, not just a award for a work. His immediate response was literally "Oh God, do I have to wear a tie?" Unfortunately, yes, you have to wear a tie. Okay, you guys, that's stop. Okay, so how many choices do you have now for an outfit? For a 3-piece outfit proper, huh? 9 times 6 times 4, again, because you have to choose 1 shirt, 1 pair of pants, and 1 tie, right? So you have 9 times 6 times 4 choices. So the product rule journal principle is as follows. Suppose you have to perform a procedure, right? Suppose you are counting something, right? And that procedure can be broken into subtasks, right? A sequence of tasks, right? A sequence of tasks, not a collection of tasks, right? A sequence of tasks. If task 1 can be done in N1 ways, and remember the underlining thing, for each way of doing task 1 you can do task 2 in N2 different ways, then the total procedure can be done in N1 times N2 different ways, right? So in the previous one, picking an outfit can be broken down into 2 tasks. First task is pick up a shirt. Second task is pick up a pair of pants. Choosing a shirt can be done in 8 ways. For each way of doing it, picking a shirt, for each possible shirt, you have 6 options to pick a pair of pants, right? And that's why it's 9 times 6 or whatever the numbers were there, right? Here is a good example from some other source. I mean, I didn't make the diagram. So you are picking up an ice cream. So this is more a pictorial way of showing you all possible ways. I'm going to give you some more of other examples. So you have 3 choices for flavors for an ice cream, 3 choices for toppings, and 3 choices for a sauce. Okay, how many different ice creams can you choose? 3 times 3 times 3, right? The first task is pick up a flavor, the second task is pick up a topping, and the third task is pick up a sauce, right? Flavor can be chosen in 3 different ways. For each way of picking, for each flavor, you have 3 choices for a topping, right? For each flavor and a topping, you have 3 ways to pick up a choice, right? You see this tree diagram? Understand this thing. This is the first task. You can either go choose vanilla, or you can choose chocolate, or you can choose banana. These are 3 choices. For vanilla, you have 3 choices for a topping, and for vanilla and each topping, you have 3 choices for sauce, right? So this way, this is the total possible ways is 3 times 3 times 3, right? 27 different possible ice creams. A more set theoretic version of this statement is that the cardinality of the cross product of 2 sets is equal to the product of the cardinalities, right? Cardinality of A cross B is equal to cardinality of A times the cardinality of B. And generally, the cardinality of the cross product of multiple sets, the Cartesian product of multiple set A cross B cross C, is equal to the cardinality of A times the cardinality of B times the cardinality of C, right? Okay, yes, please. No, sets have nothing to do with this one. These are 2 different sets. They could be overlapping and not overlapping. Okay, how many ways you can arrange the letters A and B? How many different 2-letter words can you make from the letter A and B? A and B. 2-letter words. So arrange these A and B. So that's the length is 2, right? Which 2 words can you make from A and B? AB and BA, right? So the procedure is making a word, right? Or arranging. Arrangement is a procedure, right? I can break it into 2 tasks, 2 subtasks. The first task is pick up the first letter, fill up the first box, right? And the second task is then fill up the second box, right? The second blank. How many ways can I do? Fill up the first box? 2. I can either choose A for it or B for it, right? Then how many ways can I do the second task, the second box? Actually, it's 2. If I look at it independently, I can choose, the second box can contain A or B, right? So it has 2 choices. But I'm going to look at the successive task. If I've chosen A for the first box, then can I choose A for the second box? No, right? That will be not arranging. That will be just repeating or something, right? So I have to choose for each way of doing the first task, first box, filling up the first box. I have only one way to do the second box, right? So that's why the number of different letters, the 2-letter words, different arrangement of A and B is actually 2 times 1, and namely AB and BA, right? How many ways to arrange 3 letters A, B, and C? Quickly. What is the procedure? Filling up these 3 boxes, right? A, B, C, this blank boxes, I have to fill them up. What is the subtask? Fill up the first box, or choose the first, give the first position to either A, B, and C. The second choice is, the second task is, the following task is fill up the second box. The next task is fill up the third box, right? How many ways can I fill up the first box? 3, right? Choose the first letter. How many ways can I choose the second box? 3, but for each way of choosing the first task, the first box, then I have 2 choices, 2 remaining choices for the second box, right? For each way of choosing the first and the second, then I have only one choice to fill up the third letter, right? The third box, Okay, so it's 3 times 2 times 1, that's the answer, namely A, B, A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, A, and C, B, A. Okay, so I can do 3 ways to do it. Now for each way of doing task 1, if I have chosen A, then I have 2 more ways, B and C. If I have chosen B for the first one, then I have A and C, 2 choices. If I have chosen C for task 1, then I can only choose A and B, right? So read this thing, okay, for each way of doing task 1 and task 2. And this has to be one of the things that people find very confusing about this. Oh, should I apply sum rule or product rule, right? It will be clear hopefully later also. You guys please stop talking. This row and the row behind you, last row. Okay. Okay. So how many ways can you choose A, B, C, and D? How many different arrangements can you make for A, B, C, D? Okay, first you do the break up into task. So the procedure is filling up 4 boxes with A, B, C, and D, right? And so the first task would be fill up the first box, then the second box, then the third box, then the fourth box, and the total possibilities is 4 into 3 into 2 into 1, right? These are all written here. These are all ways where the first box is given is filled by A, all ways where the first box is filled by B, and the first box is clear? 4 into 3 into 2 into 1. How many ways to arrange generally n letters? Right? Filling up n boxes will require picking up, first fill the first box, then fill the second box, then the third box, and so on, right? So it will be n times n minus 1 times n minus 2 times n minus 3 all the way up to 3 times 2 times 1, right? So generally this is going to be equal to n factorial. Okay, that's the definition of factorial also, but we'll see. Okay, suppose I have 4 CS students A, B, C, D and 3 EE students X, Y, and Z, and I want to make teams of 2 CS students, 1 EE student, right? How many different teams can be made from this? How many different teams can be made? Give me the procedure, not the answer. Give me the methodology. Where is the product rule coming from? No, tasks, yes. So I have, the team has how many people? 1 CS? Teams of 2. Okay, so it's a pair, right? So I have to choose a pair of students. So I have to fill up these 2 boxes. One box is going to be filled up by a CS student. Let's say it's the first task or the first box, and the second is going to be filled up by EE students, right? Do you see why is it different than arrangement of A and B?
Because the sequence doesn't matter.
Sequence is different?
It doesn't matter. The sequence doesn't matter.
The sequence doesn't matter, right? Each number you chose 48, so it will be 8 minus 4, 4, right? You chose 73, so that will be let's say 72, that will be 7 minus 2, 5, right? Or 2 minus 7, absolute value 5, right? Not really. So you get these 11 numbers, the number you get those 11 differences, right? The digit differences, absolute value of digit differences. Suppose I tell you, okay, and what I'm saying is first at least student, then 2 of these differences must be the same. Why? What should be the pigeons? Go ahead. Those 11 differences, what are the possible differences? How many different differences are possible? Yeah. So it's different from choosing A-B arrangement in this sense that I still have to fill up these 2 boxes, right? But the options for one box is separate, is what is it called? Is disjoint from the option for the second box, right? So it doesn't reduce those things. I think it answers your question also. Do the sets have to be disjoint or something, right? So they could be, previously they weren't, right? Okay, so break the team making process, the procedure into 2 tasks. Choose a EE student and choose a CS student, right? How many choices do I have to choose a CS student? 4, right? I can choose A or B or C or D, right? I have 4 choices. For each choice of filling up the first box, how many choices do I have to fill up the second box? 3, right? I can choose X, Y, or Z, right? So the number of ways to do it is 4 times 3, right? And these are all different teams of teams that can be made with that those constraints. Okay. Okay. Suppose you have to choose. Remember, this was the problem we did earlier also, slightly different. Suppose you have to choose a project from 4 development projects and a project from 5 research projects. How many different combinations, how many different ways one can choose a project? How many choices do you have? Do the process. Okay, how many different choices do you have? You have to choose one software development project and one research project, right? So you have to fill up these 2 boxes. The first box you have 4 choices. For the second box you have 5 choices. For each way of filling up the first box, for each software project you have 5 choices for a research project, right? And that is 4 times 5, 20. You have 20 choices. Okay, here is another how many questions. Every one of you should know matrix addition and should have done some programming with this. Adding 2 matrices of same dimensions is going to result in the matrix of the same dimension, right? Number of rows and columns. Here is an algorithm for that, right? For I equals 1 to m, this is the number of rows in both A and B, and this is for j equals 1 to n, that's the number of columns in A and B. Cij, which will be another m by n column matrix. Ijth entry of cell of C is equal to the sum of the ijth cell of A plus the sum of and the sum of and the ijth cell of B, right? How many times this addition operation, this blue operations is performed? Okay, so this is where you see these boxes thing is what we hypothetically were thinking. Now the boxes are actually real boxes, right? For each different value of I and j, for each value of I and j, you do an operation, right? So how many different values I take and how many different values does j take, that will be the number of times this addition operation, the blue statement, will be executed, right? The addition and assignment. Okay, so what are the possible, how many different values of ij? I don't want to use the word combination. How many different values of ij, choices of values of ij are there? Look, box I, the first index, filled in one of the m different ways, right? I equals 1, I equals 2, all the way up to I equals m. These are m different ways. For each way of choosing the first box, for each value of I, j takes n different values, right? So the number of operations, the number of times this blue statement is performed is m cross n. Okay? Okay, so you have a license plate. It contains 3 letters and 4 digits, typical Pakistani license plates, I hope. How many different license plates are possible? That was the MTAG questions that those idiots could not figure out. How many MTAGs, how many different license plates are possible? What are the boxes? How many boxes do you have to fill? What is the, right? So this is 7? Yeah, this is 7. Okay, so
26 cubed.
yeah, so don't give me answer. Don't give me answer. Do you everyone this way?
3 boxes for the letter.
Yes, 3. The first.
In each box, repetition is allowed.
Did you hear me use the word repetition?
We can use the same like.
Yes. So you'll see that. Don't confuse yourself, because it's going to become immediately important. The next slide is going to be there. Not the next slide, but exactly the same example. Similar example is going to come up. Okay, I have to fill up 7 boxes. 3 boxes by the letters and 4 boxes by digits, right? So now tell me, how many choices do I have for the first box? These 3 are reserved for the letters. 26 choices to fill up the first box, right? So first place, I have 26 choices. Now, for each way of filling up the first box, how many choices do I have for the second box? How many? 26. Remember you said 3 to the 3? Because you were doing, trying to answer the question. You were not discussing the question itself. You want to leave the room? Keep the phone. Okay. So we have 26 choices to fill up the first box, right? One of the A, B, C up to Z. And for each way of filling up the first box, I have 26 choices to fill up the second box, right? I'm just giving you one example filling up of the. Oh, okay, so let's LEE is not a valid license plate. It is valid, right? So I never, there's no restriction given there, right? So it says fill up 3 letters thing, and here actually 0 is repeated. You see 0 0. It's not my car, by the way. Don't break it. It's just I took a picture from, not random, but whatever Google had it, or maybe I took it from. Huh?
It's anyone's car.
Yeah, somebody's car. I don't know. It's very old car. Maybe it doesn't exist anymore. When I took the picture from Google somewhere. So how many choices, if for each way of filling up the first 2 boxes, how many choices do I have to fill up the third box? Still 26, right? For each way of filling the first 3 boxes with letters, how many choices do I have for the fourth box? 10, right? I could choose 0, 1, 2, 3, all the way up to 9, so there are 10 choices. For each way of doing the first 4, how many choices do I have for the fifth box? Fifth is still designated for a digit. It could be any of the used one, right, of the previous box, and so on. And how many choices? So this will, the total number of ways to do it is 26 times 26 times 26 times 10 times 10 times 10 times 10, right? Yes.
Sir, but थोड़ा सा ये भी नहीं होता कि अगर नंबर प्लेट 1 हो तो first 3 digits mention 0001 हो, then it's just
No. So that depending on what you are, what your rules are. My rules and my constraints are given on this slide. Okay. Then we just discussing methodology, right? Nowadays, I think they write it at least Islamabad people write this 0. If you have a number 001, then they will write 001, right? I think they do it now in Islamabad one. Okay, so 26 cubed times 10 to the 4, right? That's the way. How many 5-digit postal codes are there? Postal codes or zip codes are these 5 digits numbers that uniquely identify a location, a region, or a place, right, somewhere. How many different ways? What are the boxes? 5 boxes that we have to fill, right? So we have to pick up a postal code. We break it into, pick up the first digit for a postal code, then the second digit, then the third digit, then the fourth digit. How many choices would we have for the first one? 10. Then how many for the second one? Actually, here I'm giving you the choices, the actual choices that we have, right? We have 0, 1, 2, 3, 0 to 9. These choices are there. How many choices for each for each way of filling up the first box? How many choices do I have to fill up the second box? 10, right? The same 0 to 9 choices are there. Then the 0 to 9 choices, then 0 to 9 choices, and so on, right? So the total ways to do, how many different postal codes are there is 10 to the 5, right? So if you have, if let's say each district or each some definition of town is a total has a unique, globally unique postal code, then you cannot have more than whatever this what is it, how many, 99,000 cities, 99,999 different towns. Yes, please, somebody raise hand. Sorry? Okay, so that's a postal code. Could be, doesn't forbid us, right? It doesn't say anything. It just says 5-digit postal code. right? Even in this one 08854, that's a Piscataway zip code, it is has 8 repeated, right? How many 5-digit postal codes are there with no repetitions? Now I'm not allowed 08854. Wait, so it's the first time I'm using the word repetition. Yes. Okay, so do not break up into tasks. So I have to I have to find out number of ways to fill up the box, 5 boxes, right? So what the first box, the second box, the third box, these are the successive tasks. How many choices do I have to fill up the first box? Which choices do I have?
0 to 9.
0 to 9. I can pick up anyone, right? So that's, I have 10 choices for the first place. How many choices for the second place? Generally speaking, if I ask you in an isolated question, how many choices for the second place? Is 10. 10 choices, right? But now is a successive task, is a following task of filling up first box 1. Now for each way of doing filling up box 1, I have 9 choices to fill up the second box, right? So that's why I was always keeping a running example, because now 0 is not a choice with me. For the second box, if I have chosen 0 here, then 0 is not a choice, right? So suppose I've chosen 8 for the second one, then how many choices do I have for the third one? The remaining 8 digits, 0 and 8 are out, the remaining 8 are my choices, right? So the answer is 10 times 9 times 7 times 8 times 6, right, or whatever. Okay. How many passwords can be made with the following rule? It can contain digits and case sensitive English letters. So different English letters possibles are how many? 52, right? 26 uppercase, 26 lowercase, and 10 digits, right? It must be of length 5, 6 or 7, right? The length of a password must be between 5 and 7. It must begin with a letter. How many different passwords can be made? The question clear? The question clear? Right? Now this is slightly complicated question. So wait a minute. What is the first level of complexity from the postal code? What is the difference between this and the postal code?
3 possible lengths.
There are different possible lengths, right? Postal code was fixed 5 lengths. License plates were 6, 7 length, right? So that's the first level of complexity. And then there is this options are different, right? Then there is another level of complexity. It must begin with a letter, right? The license plate had letters, but the first 3 were letters and the last 4 were thing. So now we have many choices, right? There are many ways to fill up this thing. Yes?
Sir, apart from the first block, we can just use the sum rule again.
Yeah, wait. So we'll come to this. You had a question?
So you will have a range, it should be between, so you can have a digit, you can have a letter at the beginning, so that's 52% of choices, and then you can have 52% of choices at the beginning, and then for each of the next one you can have.
We'll come to the answer, okay? So let's just discuss the problem. We'll come to answer. Do you see that the second constraint or the second condition it brings a different level of complexity. It makes it different or maybe complicated than the previous 2 things, right? But this is 5 or 6 or 7. That's how I pronounce it. Says 5 to 7. 5 or 6 or 7 means what? Should use the sum rule, right? Should use the sum rule, because the password would be either of length 5 or a length 6 or a length 7, not both. These are exclusive disjoint sets, right? So I'm going to find different passwords. Passwords of length 5. How many valid passwords of length 5? So condition 1 is fixed to be of length 5. Condition 2 is fixed to be of length 5. Condition 1 and 3 are going to be maintained for P5, and P6 and P7 is different thing, right? So I took out 1 level of complexity, right? Simplified substantially the thing. Now the P5 is a set of passwords of length 5. substantially easier, is exactly the same as our postal code type thing, right? How many passwords are there in P5? What is the cardinality of P5? How would I do P5? Now it's product rule, right? Remember, if you didn't have sum rule, go home and try this question without using sum rule. I told you sum rule in isolation may sound like a useless tautology, but actually it's very helpful if you look at it this way, okay? If you use it in conjunction with other things. And now the more techniques we learn, the more we will practice these things. Okay, so P5 is just filling up these 5 boxes. How many choices do I have for the first box? 52, right? Because it must begin, the only choices I have is those 52 different letters, right? If I choose the letter P, how many choices do I have for the second character? 62. Now either of the uppercase 26 letters, lowercase 26 letters, or the 10 digits, right? So the number of passwords in P5 is 52 times 62 times 62 times 62 times 62, right? 52 times 62 to the 4, right? What is P6? What is the cardinality of P6? 52 into 62 to the 5th power, right? What is the cardinality of P7? 52 into 62 to the 6th power, right? Makes sense? So what is the total number of passwords?
52 into 62 power 4 plus power 5.
So look at this, the way it's written here, that P5, P6 and P7 these three make a partition of the set of all valid passwords. A partition. Partition is a very important word. Remember, we said a partition of a set is splitting it into disjoint sets that cover all of them. So the union is all passwords. I can make very easily disjoint sets, but if the union is not the universal set, then it's not a partition. Okay, so this is a partition, means all the passwords are contained, all the valid passwords are contained in exactly one of them. No valid password is out of these 3 sets, right? It's a partition. So I can just add these things. I have the numbers, and I can will give me the answer of all valid passwords. Okay. Okay. So I want to give you one more quick simple thing. It's called some of you initially the sum rule said, okay, find the thing. So this is a very simple one. By the way, you have a midterm quiz somewhere next week, right? Thursday? Wednesday? Okay. So we will finish counting hopefully before that. Most of counting will be done in the next Monday class, and then maybe an advanced topic will be left that we'll cover on the day of the quiz, but that will not be included in the quiz. Okay, the rest everything will be included. Cardinality, induction and counting, most of it. So maybe this one will remain for the last thing. Can you please pay attention to this? Okay, so the product rule is a really simple thing. You want to count the elements of A, you instead count the elements of A complement, right? A very simple common sense application. This is the thing we discussed earlier. And how many, if I roll 2 dice, a blue and the red dice, in how many outcomes the 2 dice show different value, right? We saw the answer was 30. We did it through sum rule, right? So now I want to do it through the complement principle. Okay, suppose I roll a red die and a blue die, and I count in how many I want to count how many dice, in how many outcomes the dice show different value. So S is what I want to find out. So instead of that, I count B, which is the set of all outcomes where the dice show same value, right? The dice show same value. How many are these? 6. Why? Which 6 are outcomes? Which they? 1 1 2 2 3 3. It's easier to count, right? So then I can count just 36 minus the cardinality of b, which b is 6. So 36 minus b is 30, exactly the same answer as we got earlier, right? Now this becomes extremely important in some cases. So how many 5-digit postal codes are there with at least one repetition? Remember, we know how many postal codes can be made with. Generally, it was 10 to the 5. Then we said how many 5-digit postal code with one repetition? That is 10 with no repetition is 10 times 9 times 8 times 7 times 6, right? We just did it. So how many are done with at least one repetition? Try to do it with the product rule without using the complement principle. Try do it, not now. You go home, try doing it without the sum rule, right? The complement principle. So, but this is very easy if you do it. How many total 5-digit postal codes? 10 to the 5, right? How many 5-digit postal codes are there with no repetition? 10 times 9, no, not 10 factorial. 10 times 9 times 8 times 7 times 6, right? How many with at least one repetitions? All codes minus those with no repetition will be having 1 or 2 or 3 or 4 or 5 repetition, right? So the answer is 10 to the 5 minus 10 times 9 times 8 times 7 times 6, okay?